Right, guys, let's get started. Okay. Can you guys hear me?
Yes.
Okay, great. Okay, so just a quick recap on what we discussed in the last lecture. We move on and basically talk about the other transport mechanism, which is the diffusion process, and this basically results from a concentration difference in your semiconductor, and we derive two current density equations for the diffusion current for holes and electrons, and we see that this is proportional to the gradient of the concentration in the semiconductor. And we noted that there is actually a difference in the sign in the equation, okay, where in the case of the holes, the sign that you get in the diffusion current is negative. In the case of electron, it's positive. And we learned that this is essentially because of the difference in the direction that the carriers actually flow, or rather the difference, between the conventional current and the direction in which the carrier flows, okay, given a concentration gradient. As a result, you get a difference in the sign in the conventional current that you derived, okay? So in general, when you look at a semiconductor device, the current density that you get in the semiconductor, it's essentially made out of 4 components. Okay, 2 are due to electrons having the 2 transport mechanisms, the drift and diffusion, and the other 2 will be due to the holes, with drift and diffusion. Of course, whether these current components exist or not depends on, whether you have electric field in the case of drift, and whether you have concentration difference in the semiconductor for the case of diffusion. All right, but in general, the current that will contribute to what you measure, right, in the semiconductor is essentially due to these 4 components, right? So the total current is the sum of these 4 components, right? Now we also touch on the Einstein relation, which give us a link between the diffusion and the mobility process, and we see that they're related by this KBT expression here, and we kind of explain that the reason for their relation, right, it's essentially because the drift and diffusion process is essentially limited by scattering in the semiconductor. Okay, so they actually have a common factor, right, between the drift and diffusion, which is scattering that limits how fast the carrier can move, and consequently you get this relation that you can apply to find out one parameter from the other. Okay, the temperature. So this is actually useful in the case where you're given one parameter, say mobility, and you want to determine the diffusivity, right? Then you can apply the Einstein relation to work out the corresponding parameters. Okay. Now we also cover 2 characterization technique that is commonly used in semiconductors to basically measure the sort of parameters of your semiconductor materials and the carriers. Okay, we talk about the Hall effect, which is an experiment where you bias the semiconductor along one direction, and then you place this semiconductor in the presence of a magnetic field, and we measure the voltage in the other direction, right, the lateral direction. And from such measurement, we can actually determine a couple of things about the semiconductor. The first being the carrier type, okay, the majority carrier type that is present in the semiconductor. The second will be your majority carrier concentration in the material. And from this experiment, you can also determine the carrier mobility. Okay, so there's actually a couple of things that you can actually determine from this single measurement. Okay, so it's a common characterization tool that's used, okay, to determine this device characteristics and the semiconductor properties, right? The other characterization technique that's commonly used is the 4-point probe technique. which is effectively a resistance measurement technique. And we talk about why we don't use the conventional 2-point probe measurement to measure resistance of a semiconductor. And the bottom line is because in those measurements, you actually have some unwanted resistance, right, that would actually distort your measurement. Okay, because in those measurements, the two unwanted resistance, the contact resistance and the spreading resistance, would generally be significantly more than that of a semiconductor resistance. Okay, because typically semiconductors are fairly heavily doped, so the resistance is fairly small. Okay, so if you use a standard 2-point measurement technique, right, then you would quickly realize that the resistance that you measure is not the true resistance of the semiconductor material. Okay, and the way to overcome this is to basically adopt this different measurement configuration called the 4-point probe technique, which uses 4 contact points, okay, the outer which is connected to essentially a current source, that drives current through the semiconductor, and the middle probe is used to measure the voltage dropped across the semiconductor. So, and the middle probe basically uses a voltmeter, which effectively doesn't draw current from the semiconductor, and that actually illuminates the effect of contact resistance. Okay, contact resistance will show up if you have current passing through the probe into the semiconductor. So if you don't draw current, then contact resistance it's eliminated, right? And at the same time, because we're measuring in an inner portion of this current that's driving through the semiconductor, okay, the part where the probe delivers current into the semiconductor, where the spreading is occurring, is also avoided because you're measuring the middle part of it where the current has become sort of parallel, right, to the surface of your wafer. Okay, so this type of measurement, it's although it's very quite simple, right, it avoids the effect of this unwanted resistance of contact and spreading. So such measurement can allow us to determine the resistivity of the semiconductor, which then in turn allows you to derive the impurity concentration or the majority carrier concentration. And from the measurement itself, right, we can also use the quantity that's measured to determine the carrier mobility in the semiconductor material. Okay, so again, these are like electrical properties of the semiconductor which are important, to know. So anyway, in lab 2, actually one group has done the lab 2 already, so we'll actually be doing this 2 experiment, all right, to see how these are actually applied to measure all these parameters of the semiconductor. Okay, then the last thing we did was to talk about the last topic for my part, okay, which is pertaining to non-equilibrium condition in the semiconductor. So far our discussion has been sort of centered around equilibrium condition, where the semiconductor does not have any external force that's applied to it, whether in the form of electric field or magnetic field, okay, or temperature difference, right? Everything is in equilibrium, thermal equilibrium. So because in practice, when you use a semiconductor material in the form of a device, usually when you drive it, right, current starts to flow, the conditions are usually in non-equilibrium, okay? So we need to also know how to analyze these non-equilibrium conditions in semiconductors. And we mentioned 2 specific conditions that it's commonly encountered in semiconductor devices. First being the optical illumination, right? When you shine light on a semiconductor, you create extra carriers, okay, and we don't know how this extra carriers changes, okay. And the other non-equilibrium condition is regards to external bias. Okay, suppose you bias a semiconductor by injecting current into a semiconductor, so carriers actually goes into a semiconductor, and that leads to a non-equilibrium condition. You want to know how the excess carrier behave, okay, in the semiconductor, right? This would subsequently we in fact used in the second half of the course, where you use it to analyze currents, okay, that is flowing in PN junction diodes. Okay, so that's why we need to cover this first. So in regards to the first non-equilibrium condition pertaining to shining light on the semiconductor, okay, here we are essentially talking about shining light uniformly, right, to a semiconductor material. That means you illuminate every part of the semiconductor with the same amount of light intensity, okay? And so in doing that, in general, right, other than your thermal generation, the GTH, okay, which in our sort of discussion, right, we say that it is actually equals to alpha R Ni square. Okay, alpha R is, you can think of it as a material parameter. Ni is the intrinsic characteristics of the semiconductor, okay, which as you see earlier depends on band gap and temperature. Okay, and what it simply means is that the thermal generation rate, okay, the amount of carriers that generated per unit volume per unit time, is dependent on the band gap and the temperature of the semiconductor, right? And notice that it doesn't depend on the doping. Okay, regardless of the doping, this thermal generation rate is the same. Then the other process, right, that serves to cancel out the carriers, right, to reduce the carriers, is the recombination. This is again a natural process where you have electrons and holes in the semiconductor. The electrons and holes will have a chance that it would return back to the valence band and cancel out a hole there. Okay, and this recombination rate, it's actually a function of the number of electrons and holes you have in the semiconductor, which makes sense, right? Because you have a larger number of these electrons or holes, then there's a higher chance that a hole or electron can see one another, right? And then the rate at which they recombine will also be higher if your concentrations are higher. Okay. So in addition to this two sort of process, right, that can change the concentration of carriers, that's actually this optical illumination one, which helps to increase the number of electrons and holes, right, that will come in now under the optical illumination consideration. Okay, so with these three components, right, how do we describe the change in the concentration of electrons and holes? Okay, our ultimate aim here is to find out what is delta N, delta P as a function of time. Okay, because here we are illuminating the semiconductor uniformly everywhere. So if there's an excess carrier that's created at one location, right, you expect the same to be created at other location as well, because the illumination is uniform. Okay, it's the same everywhere. So to describe this change in the concentration of carriers, okay, we use this equation here, which we call the rate equation. Okay, it's basically describing how electrons or holes change with time. In this case, if you assume that this is a p-type semiconductor, then we look at dn dt. Okay, if you have a n-type semiconductor, then usually you look at the minority carrier, which is dp dt. Okay, so this rate of change of the carriers will depend on these three terms now. Okay, because you now have optical illumination. So the thermal and the optical illumination GL serve to increase the number of electrons and holes, okay, per unit time. The recombination one actually would decrease it, so it's subtracted from the terms. Okay, so there's a generation process comprising the thermal and the optical illumination, and there's a recombination, which is the sort of natural process that cancels out the electrons and holes. Okay, so we can use this differential equation, right, to try and determine what is delta N or delta P as a function of time under different scenario. Okay, so we sort of mentioned three scenarios that we'll be analyzing, right? The first is essentially the trivial case, which is the thermal equilibrium. So without optical illumination, obviously the excess carrier delta N will be 0, and your concentration of your electron in this case for p-type semiconductor will be N0. Okay, so that stays a constant, okay, under thermal equilibrium condition. And suppose at some time t, right, you turn on the light, okay, then the GL now comes in, right? It provides a additional generation source, and you expect extra carriers to be created. Okay, and if you turn on the light for a sufficiently long time where it achieves steady state condition, then what you find is that the concentration of your electron would actually stabilize after a while. Okay, So the question is, what is this delta n value, okay, on top and above of the n naught value under thermal equilibrium? Okay, what is this extra value here? So using the rate equation, we see from our last discussion that this leads to extra carrier delta n, okay, that is given by the optical generation rate GL multiplied by time quantity called the minority carrier lifetime tau n naught, okay, which basically describes how long the minority carrier would exist in the semiconductor before they recombine and disappear. All right. Okay, so it's just a product of the optical generation rate and the minority carrier lifetime. Okay, to find out what's the steady state concentration of the excess carrier delta n. Okay, so today we're going to basically talk about the third scenario where when the semiconductor is illuminated with light and you achieve steady state, right? What happens when you switch off the light? Okay, so if you switch off the light, okay, this GL now is gone, right? And you have extra carriers which will obviously start to recombine more than the generation, and as a result, you actually find that the delta n would decrease. Okay, you start to decrease with time, okay, with a certain rate until it eventually goes back to thermal equilibrium condition n naught, okay, which is what you expect, right? Because if you don't have the optical illumination, then the concentration of your electron, okay, in this case, would be going back to the thermal equilibrium value n naught. Okay, so we expect this to decrease until it goes back to n naught. Okay, so let's now look at your rate equation to see how we can analyze that to get the equation for this profile here, okay, as a function of time. So, okay, so the way to analyze this will be, of course, using the rate equation. So here we are, again, assuming that we're looking at a p-type semiconductor, right? From the figure, you can see it's quite obvious. The p naught, it's more than your n naught, so it must be a p-type semiconductor, and you have this extra bunch of excess carrier, right? So if you apply the rate equation, dn dt equal to gth plus gl minus r. Okay, when you switch off the optical illumination, obviously your GL must be equal to 0. So, okay, so this term here will basically disappear, right? And that leaves us dn dt equals to gth minus r. And this dn dt term is not equal to 0 because it's not in steady state, it's not in thermal equilibrium, right? You're expecting it to change with time. So this is not 0, you cannot equate to 0. Okay, so we need to use this, right, and try and solve for, remember the objective is to find delta n, okay, to try and find out what is delta n. Okay, so this term here, if you look at it, with the dn dt, this is really a first order differential equation. Okay, so let's try and solve this to see what solution you get. So with the two terms, right, the gth minus r, okay, we can put in the respective terms. Okay, this alpha r ni squared, that's your gth, and the other term alpha r np, that's the recombination rate r. Okay, and as we have seen previously, the n and p is really your n naught plus delta n and p naught plus delta p. So this delta n, delta p is not 0, right? Because when you just switch off, they'll have some value and they will change with time. Okay, so they do not equate to 0. So you need to keep that there. And if you multiply out the terms, you'll find that one of them is n naught p naught, okay, which is your ni square. And this would cancel off with the ni square you have from gth, leaving us 3 terms now. Okay, like what we have for the second condition that we are analyzing, right? So similarly, the optical illumination will produce the electrons, excess electrons that holds in pairs, implying that delta n, delta p are actually equal. Okay. And since in this case our variable is n, replace the delta p with delta n, and it gives us this expression here. We can take out delta n as a common factor, So applying our two conditions, right? Remember, there's two conditions that we used in analyzing the second scenario. Okay, one of which is the majority carrier are much greater than the minority carrier. So in this case, majority carriers are the holes. Okay, so that means P naught is much greater than N naught. Okay, and this implies that the N naught is negligible. Okay, we can ignore that. And the other assumption is that your excess carrier, right, is a low injection condition. The excess carrier is much smaller than that of the majority carrier P naught. Okay, and that will imply that the delta N in your bracket is also negligible, leaving us just one term, the P naught. Okay, so this allows us to simplify our first order differential equation to just a single term on the right hand side. Okay, so if we do that, then we have just minus alpha r P naught delta N. And remember, we say that this quantity here is inverse time, right? So we denote this as 1 over tau N naught. Okay, and we mentioned in the last discussion that this is your minority carrier lifetime. So we're going to see why that is so, okay, after we get the solution for this. Sorry. Okay, so the other thing that we can also simplify is this N here. Okay, so in the differential equation, we have variable N, but on the right hand side is a variable delta N. Okay, so we can replace the N with N naught plus delta N, right? And if you do a derivative of this with respect to time, then the N naught actually will be 0. Okay, so in other words, the dN dt is essentially the same as d, right, delta N dt. Okay, because the N naught is a constant, doesn't change with time. So if you differentiate that, you get 0, right? So the thing that's changing is actually the delta N. So we can actually write this equation as the derivative of delta N over dt, right, equals to minus delta N over tau N naught. So this is the first order differential equation in delta N. If you can't sort of visualize this in the variable that you've been using in H2 math, right? If you write it as dy dx, you know, then this is like dy dx equals to minus y over tau N naught. Okay, so how do you solve for y in this case, or how do you solve for delta N in this case? Okay, so there's a delta N on the right hand side, so we can separate the variables and keep delta N on one side and dt on the other side, right? So we do a variable separable, right? And you group all the same terms on the respective side. Okay, so if we do that, you basically will bring the delta N to the left hand side, okay, which will end up in the denominator 1 over delta N, and you have the derivative of delta N, right? And on the right hand side, we bring the dt over. Okay, we can keep the 1 over tau N naught on the right hand side. Okay, that gives us a form that we can actually solve. Okay. Okay, so you can solve the first order differential equation by separating the variables. Okay, grouping them to the same side. So for the integral of 1 over delta N d delta N, this will just give us the natural log, right, of delta N. Okay, and the right hand side, you know, what you have there is a constant. So if you integrate that, you have just 1 over tau N naught. Okay, multiplied by t because it's just a constant, and then plus some c. All right. So if you then apply the boundary condition, okay, where suppose at the time when you switch off the light is t equal to 0, okay, the concentration of delta N is basically equals to the delta N at time t equals 0, right? So we write as delta n 0, and if you substitute into this solution, right, and find out what's c, okay, the final solution for delta n as a function of time will be this, okay, where the delta n of t is equals to delta n at time t equals 0. We just switch off the light, and you notice that it decreases exponentially with time, okay, and there's a characteristic sort of time parameter there, tau n naught, okay, which kind of describe how quickly the excess carrier will decay. Okay, that's why this term here, tau n naught, is called the minority carrier lifetime. Okay, it sort of quantify how quickly this excess carrier would decrease and disappear, right? The larger the value, the steeper the exponential curve. That means it decreases faster, right? Okay, we will try and draw the delta n profile, okay, as a function of time. Okay, so obviously if your tau is large, then this will go down very quickly, right? So this is, let's say this is tau 1 versus another case where, let's say your tau is smaller, then it will take a longer time for it to decrease to 0, right? Let's say this is tau 2, okay, where of course tau 2 is smaller than tau 1. Okay, so this tau value in your denominator in the exponential function is a characteristic time. Okay, it's like a decay time. All right, that's why we call this a minority carrier lifetime. Okay, so it's basically just a simple exponential function, right? Bringing the extra concentration back to 0. And of course, you know, with the optical illumination, we see that at steady state, your original excess carrier concentration is GL tau n naught, right? So we can actually put this into the equation as well as the starting value. Okay, so the equation is, you know, for this case, would effectively be, okay, we put in the delta n at time t equals 0, right? Then this will be delta n at time t. Okay, it's just equals to the GL times tau n naught, right? If it's come from a situation where you first switch on the light and you let it achieve steady state before you switch off, then that's the equation you can use. Okay, with the delta n at time t equals 0 as GL tau n naught. Okay, so that's the equation for the change in your excess carrier when you switch off the light. All right. So similarly for n-type semiconductor, with the host as a minority carrier now, right? You apply the same consideration with the two assumption right here, pertaining to the difference between the minority and majority carrier and the magnitude of your excess carrier. Okay, which you know, in which we assume a low level injection condition, then you can similarly derive the minority whole excess carrier equation, okay, for the n-type semiconductor where you just switch off the light. And of course, in this case, the characteristic time for the decrease in the excess carrier now is tau p naught, which is the excess minority carrier lifetime. Okay, holes in this case, right, is a whole minority whole carrier lifetime in the semiconductor, and it is related to the concentration of your majority carrier in the semiconductor. Okay, so this basically describes, you know, how the excess carrier changes with time. Okay, when you switch off the light in this consideration. Okay, let's see how we can apply this to an example. So in this case, let's say we have a piece of p-type semiconductor, and your accepted doping is 10 to the power 15. Intrinsic carrier is 1.5 by 10 to the power 10. So this kind of tell us that this is really a silicon sample. Now, this question, you are told that 10 to the power 14 electron hole pairs are created and exist in the semiconductor for t less than 0. Okay, so this is your delta N, delta P, and the minority carrier lifetime is 10 nanosecond. Okay, which means that the minority electron carrier lifetime is 10 nanosecond. And you remove the excitation at time t greater or equal to 0. What is the excess carrier concentration for t equal to 10 nanosecond, 20, and 30 nanosecond, and to infinity? And you're supposed to plot the carrier concentration versus time, okay, to show the decay of the excess carrier and comment on the percentage change of the carrier concentrations. Okay, so if you assume that in this semiconductor there is complete ionization of the impurities, and of course we see that your Na is much greater than Ni, then the majority carrier concentration P0 can just be written as equal to the acceptor concentration, okay, which is 10 power 15. And the initial excess carrier concentration as given in the question is 10 to the power of 14, okay, which is 0.1 times that of P0. Okay, so the excess carrier compared to the majority carrier concentration is 10 times lower. Okay, so we can treat this as a low-level injection. Okay, so as a general rule, we consider the injection as low level if the excess carrier created is at least 10 times less than the majority carrier. Okay, so we use 10 as a reference. If it's less than 10 times, then we can treat it as a low-level injection. So if it's low-level injection, and obviously your P0 will be greater than N0, right? Because the P0 is relatively high, 10 power 15. You can find the N0, right, just to double check, but you'll find that P0 will be much greater than N0, which implies that the two assumption is valid, and we can just quote the solution, okay, from our discussion earlier. Okay, so this falls under the third scenario, where you switch off the light after steady state condition, and the excess carrier will basically decrease exponentially with time, starting from the initial steady state value delta N of 0. Okay, then in this case, it's characteristic time of electron. So this initial carrier concentration, it's 10 power 14, right? And obviously, it's if it's a direct band-to-band transition, then you have delta N of T equal to delta P of T. Okay, the two should be the same. So once you have this expression, then you can stick in the various time, okay, that is required to calculate the excess carrier concentration. So you put that in, you can basically determine how the concentration change with time. Okay, and particularly at T tends to infinity, right? Then in your equation, right, if time goes to infinity, then this term here becomes very, very large in terms of magnitude, but there's a negative, so that means it tends to negative infinity, and if you take the exponential of that, it would actually tend to 0. Okay, so when time goes to infinity, your excess carrier concentration would disappear, which is what you expect. Okay, because once the external source is gone, okay, then you expect the carrier concentration to drop back to thermal equilibrium case, where delta N, delta P will be equal to 0. And so if you actually draw a diagram to see how the concentration varies, okay, with time, then this is kind of what you get. Notice that in this case, the vertical axis, all right, this here is not linear scale. It's actually on a scale called a log scale, okay, where the values increases, okay, from the major divisions, right? It increases by a factor of 10. Okay, from here to here, for example, it increases by a factor of 10. This is another factor of 10. Okay, and the small divisions in between, right, are sort of integer increment of the base values. Okay, so if this is 10 power of 14, okay, this second division here will be 2 times 10 to the power 14. This is 3 times 10 to the power 14. That's 4 times 10 to the power 14, and so forth. All right, so we find there's a total of 10 of them, and when we reach the 10th 1, right, is the next big division, okay, which will bring it to 10 to the power 15. Okay, so obviously this is not a linear change in the value, it's actually a logarithmic change. It's a log scale, okay. It changes by a factor of 10. So in fact, in the experiments, you also be using graphs like this. Okay, so every big division, it changes by 10. Now you can see that in the case of the majority carrier, the excess carrier that is introduced, it's actually relatively small compared to the majority carrier. So you see that this difference here is not very large. Okay, it's approximately still a straight line. And on this log scale, right? Okay, of course we know that this, minority carrier concentration would change exponentially with time, but if you put it on a log scale, if you take the log of an exponential function, you just get a linear change, right? You just get a straight line instead. Okay, that's why this curve here is a straight line. Remember this delta n, right? Right. If you look at the equation, this changes as the exponential of some t, right, over minus tau. Okay, so if we take the log of this, okay, we take the log. Okay, let's say just for simplicity, if you take the natural log, then this just becomes minus t over tau n naught, right? So it's just a linear function of time now. Okay, that's why you see a straight line in your log graph. Okay, so that's the reason why you see a straight line there. And in any case, right, this will basically decrease quite significantly compared to the thermal equilibrium value. Okay, thermal equilibrium value is actually very, very small. In fact, if you work it out, you should get about 2.25 by 10 to the power 5. So it's sort of way down in the scale, right, in the vertical scale. Okay, so this actually will drop all the way to the thermal equilibrium value of the minority carrier when you switch off the source, okay, in this case. So for majority carrier, the excess carrier actually will not make a very big percentage of it, all right? Whereas in the case of minority carrier, the excess carrier, contributes significantly to the minority carriers. Okay, it actually makes up a very, very big fraction of the minority carrier. Okay, so in summary, right, we have this 3 scenario that we have analyzed for thermal equilibrium. Okay, which is a trivial case. The delta n obviously is equal to 0. When you turn on the light and the concentration in the semiconductor stabilizes, then we find that the concentration of excess carrier is given by the optical generation rate, GL, multiplied with the minority carrier lifetime. Okay, and that's provided the 2 assumptions are valid. Right, the assumption that majority carrier is much greater than the minority carrier and that the excess carrier is very small compared to the majority carrier. Okay, if these 2 conditions are true, then we can apply this solution to calculate the steady state excess carrier in the semiconductor under this scenario. Now, of course, the next one is the one that we just discussed, which is after steady state, if you switch off the light, then we see that analyzing the rate equation, we get this exponentially decaying function, okay, which, is eventually will go back to 0, back to the thermal equilibrium concentration in the semiconductor, right? Now, you will notice that other than this 3 scenario, in fact, there is another scenario that we didn't discuss, which is this initial part here, where when you first turn on the light, right, you see that the excess carrier actually increases until it stabilizes. So the question is, what is this expression here? Okay, how does delta n change with time from the time when you just turn on the light to the time where it stabilizes? Okay, so similarly, in fact, you can apply the rate equation and analyze this and try and derive an expression for delta n as a function of time. Okay, so I'm going to leave it to you as homework to do, right? Okay, the question here is, can you analyze this part here? Okay, to work out what is delta n as a function of time. Okay, applying what you have learned so far about the rate equation, right? Okay, you can try and derive this and determine what is this function. Okay, a hint to you is that this is in fact quite similar to that of the switching off light case, right? This function that you will get is also an exponential function. Okay, but obviously looking at shape, you should derive that it's an inverted exponential function, right? So this increase here is actually an exponential increase in the value. Okay, so try this derivation on your own, and if you have any questions or clarification, you can bring out during tutorial class. We can talk about this. Okay, we can discuss the derivation if you face any difficulty. All right, so go back and try and derive this.
Hello, Professor.
Okay, yeah, sure.
For the previous one, the generation, can I assume the generation rate due to illumination is constant? It's independent of other factor.
For which one? The scenario 3?
No, the generation, the
optical generation.
Yeah.
The
from the moment illumination is turned on,
yes,
so it reaches the steady state.
Yes.
At this period, can I assume that illumination rate is a constant?
Yes. In fact, in this discussions that we have, we are basically treating the GL as a constant. So it's a constant illumination.
Okay.
Yeah.
Thank you.
So GL is a constant. You treat GL as a constant.
Thank you.
Yeah. Okay, so the next thing that we're going to talk about pertains to the second non-equilibrium condition. So remember, for the second non-equilibrium condition, if you recall, right, I sort of briefly mentioned, this relates to the case where, let's say I have a semiconductor and, I can inject carriers in the semiconductor at one end. Okay, so if we do that, then what's going to happen? You have a lot of extra carriers that will be produced, okay, at the edge. And we have this extra carrier. What happened to these carriers here? They would obviously start to diffuse, right, in the semiconductor. And they don't just diffuse, right, because once they diffuse, then, there are extra carriers that's above the thermal equilibrium value. And other than diffusion, they will also recombine as they diffuse into the semiconductor. So you get two effects going on. You have diffusion occurring and you have recombination occurring, okay, for these extra carriers. So again, similar to the first non-equilibrium condition under optical illumination, we are interested to find out how the extra carrier, right, let's say this is a p-type, okay, so how the extra carrier delta n changes with position in the semiconductor. Okay, obviously the time could be a consideration as well, right? That there could also be a variable that will describe how the delta n change. Okay, in fact, there's actually two variables. But in the context of this discussion here, in fact, we're assuming a steady state case where, it doesn't change with time. Okay, so that simplifies the analysis, right? But anyway, so under this situation here, if you try to apply the rate equation, then you're going to have a problem, right? Because here, with the presence of diffusion, right, effectively we have current, okay, current that is changing in the semiconductor. Okay, so if we look at the rate equation, it has consideration for thermal generation, optical generation, if you shine light, recombination, which is an inherent property of the semiconductor, but there isn't a term that describes the effect of current flow. Okay, so current flow is another thing that, in fact, the rate equation doesn't take into account. Okay, the current flow could be an issue because if you think about it, right, let's say you consider this point in the semiconductor. If let's say the current that flows in here, okay, into this small element versus the current that's flowing out is different, right? If let's say there's more current flowing in than current flowing out, then that will basically imply that, the concentration in this element here must be changing. Okay, for example, if you talk about holes, right? If it's holes flowing, right? Okay, so holes flowing in is not the same as holes flowing out. That means there's an accumulation of holes in this element, right? Which means that the delta N or delta P in this element here would increase in this case, right? It will change, which the rate equation doesn't take into account, okay, the current flow. Okay, so we need to also take into account this effect of current flow, right, to complete the whole analysis, okay? So here we're going to see how the presence of a current flow can affect the concentration of carriers in some element in a semiconductor, right? This is important because in this second non-equilibrium condition that we're considering, there's actually current flow now. Okay, so we need to know how it changes the excess carrier. Okay, so we actually do a derivation of this. So suppose in this case, we look at some semiconductor sample where there's a current that is flowing, whole current that's flowing, okay? So let's say this element here has a dimension of dx, dy, and dz in the semiconductor. And suppose the current that's flowing, right, it's just in the x-axis direction. Okay, so on the left-hand side of the element, okay, this box, the current that's flowing in is Jp of x. Okay, and let's say the current that's coming out on the other end, okay, at x plus dx is Jp x plus dx. Okay, so we want to determine, with the effect of this current flow, if these two terms are different, right? How would the delta P be affected? Okay, how would the holes in this element here change with time? Okay, because of this imbalance in the current going in and current coming out. Okay, so first we can define a quantity, right, which describes the number of holes flowing into the volume element here per second. Okay, so we write this as gamma P at position x. So in other words, what is the number of holes, right, that's entering this phase of the volume element? Okay, the number of holes that's sort of crossing this area here into the box, right? So we basically divide the current density with the elemental charge. Okay, this would tell us how many holes is flowing into the area, into that phase per unit area, and the cross-sectional area of that phase will be dy multiplied by dz. Okay, so we multiply that in as well. Then we get the total number of holes that's going into this box per unit second, okay, or per unit time. All right, so we have gamma px, amount of electrons that's flowing into the box. So similarly, we can define how many holes actually leave the box from this other phase here, right? Because if you know what's the current, okay, that's coming out from this phase, Jp x plus dx, then similarly we can divide this by q and multiply by the cross-sectional area dy dz to find out how many holes are actually coming out of the box. Okay. So in fact, if you apply the Taylor series expression that we mentioned earlier, okay, we can express Jp x plus dx in terms of Jpx and the derivative of Jp respect to x multiplied by dx. Okay, so with this, we can rewrite the number of holes that's flowing out from the right-hand side of the box as a function of this Jpx. Okay, so we do an approximation to relate the current density that's coming out from the right-hand side to the current density on the left-hand side. Okay, using this, derivative terms. Okay, pretty much the same as what we did previously for this diffusion current derivation, right? So the change, right, the change in the whole concentration in the volume element, okay, which is defined as the change in the whole concentration as a function of time, okay, in the element, okay, the total element, okay, which has a volume of dx, dy, dz. So you multiply by the volume, you get the total number of holes that is changing in that volume element, okay, because you multiply with the volume already. So what we're left with in the numerator here, right, it's no longer just number of holes per unit volume, but just number of holes, okay, per unit time. Okay, you have a derivative of time in the denominator. Okay, by the way, this Greek symbol that you see here, right, it's basically used to denote partial derivative, okay, to denote partial derivative. So in the case of a single variable function, right, like say y equals to f of x, okay, we can basically differentiate this dy dx to find the gradient, right? So this is you know, simply just the derivative of the function with respect to x. Okay, that's for a single variable function. Now in the case of function that has multi-variable, okay, like for example in this case the current density, okay, this is no longer just depending on x, right? In fact, in this case, this current density is actually dependent on two variables, as we mentioned earlier, right? It's a function of position in the semiconductor. It's also a function of time as well, right? Time is also one of the variable. So if we try to differentiate this with respect to one of the variable, okay, we do what we call a partial derivative, right? We differentiate this with respect to just one variable. Okay, so we indicate that we are doing a partial derivative using this this Greek symbol delta instead of d, right? So in this case, we differentiate this partially with respect to x. Okay, that's why here we write it as this delta. We use this delta symbol to indicate that it's a partial derivative. All right, so this is applied for multivariable functions. Okay, that's why it's. But bottom line is it's still differentiation, right? So this is basically still differentiating the function. In this case, with respect to variable x. All right. So bottom line is it's just differentiation. Okay, so it's not something that's difficult to understand. It's just differentiation, except that it's differentiating a multivariable function with respect to one of the variable. Okay, so so on the left hand side here we have the change in the hole concentration. You know, the rate of change of hole concentration with respect to time multiplied by volume. This gives us the change in the hole in that box per unit time, right? And obviously the change will be, you know, the difference between the increase, which is due to the current that's going in on the left, right? And the current that's coming on the right will remove holes. So the difference between the two will tell you what's the rate of change of holes due to the current. Okay, so you come back to this figure, right? Okay, so this current here would have holes going in, right? You lead to holes going in, and this current on the other side, right? The hole will go in the same direction. So this leads to hole coming out. So the left-hand side component would add on holes to the box, right? And the right-hand side component will actually take out holes. Okay, so the net difference between the two will tell you how much holes is changing per unit time. For example, if on the left-hand side, right, you have 10 holes added per second, right-hand side you have 5 holes taken out per second. So there's a net change of 5 holes per second to the volume here. So the holes actually increases 5 at a time per second, right? Okay, so this expression here is basically to describe that. Okay, this expression here is to describe that. There's a difference between the gamma on the left and the gamma on the right. And if you put in the respective expression, right, with the Taylor series expansion, then obviously you can see that this term here would cancel out. And what you have left on the right hand side is 1 over q, the derivative of the whole current density with respect to x, partial derivative, and then you have your dx, dy, dz. Okay, this 3 terms here is really the same as the 3 terms on the right, so we can get rid of this. And that leaves us just this very simple form where it says that the rate of change of the whole concentration with respect to time right, the derivative of it is equal to the derivative of the current density respect to position. Okay, so this is how the presence of some current will affect the change in your concentration of the carrier as a function of time. Okay, so this allows us to in fact modify the rate equation that we have or that we used earlier to take into account the effect of current. Okay, so we now write the rate equation as this, right? We modify it to take into account the effect that, you know, it is dependent on position and time. Okay, so on the left hand side, the derivative is the whole concentration as a function of position and time. Okay, and we do a partial derivative with respect to time, right? That's in the rate equation, right? And the right hand side, other than the three terms that we have used, okay, we need to add in this additional component which accounts for the effect of current flow. Okay, so in the case of holes, the current flow would change the rate of change of hole concentration by this term here, -1 over Q, and the partial derivative of the current density of holes with respect to position. Okay, so this equation here is called the continuity equation for holes. Okay, this is called the continuity equation of holes, and really the rate equation is a subset of this, right? The rate equation is a special case of this where there's no gradient in the current that's flowing in the semiconductor, right? If there's no gradient, then this last term here actually goes to 0, right? If there's no gradient, then you simply get back the rate equation. Okay, so this continuity equation is really the general equation, and the rate equation is a subset of that, right? So similarly, you can, in fact, do the same derivation for electrons as well, right? Using the same model where we consider some volume element in a semiconductor where you have electron current flowing. But when you do the analysis, you need to bear in mind that there's a difference, okay, in terms of the flow of electrons and the conventional current. So on the left-hand side, if you have current flowing in, then, you know, in reality, it's electron coming out of the box. And on the right-hand side, the current is coming out, but, you know, in reality, electrons is going into the box. Okay, so you need to take into account this difference. And if you derive the effect of current on your change in the electron concentration with respect to time, right, then you'll find that it gives you a somewhat similar expression, okay, except that the sign is reversed. Okay, in the case of electron, the sign of this current effect, right, is positive. Okay, whereas in the other case, it's negative, which is expected because the particle flow for electron is opposite direction to conventional current. Okay, so everything is reversed, right? Okay, so this equation here is known as the continuity equation for electrons. All right. Okay, so in terms of derivation for the electron part, again, I'm going to leave it to you to work it out on your own. Okay, so if you follow the discussion for whole continuity equation, if you follow the same approach, right, you should be able to also derive the contribution due to current in the case of electrons. Okay, Ken? Okay, so perhaps let's go for a 10 minutes break, and then we'll come back later and finish the other half of the discussion. Okay, let's go for a 10 minutes break, come back at 5:15. Okay, let's come back to our discussion. Can everybody hear me?
Yes.
Okay, great.
Yes.
Right, thanks. Okay, just to make sure that everybody can hear me. If not, I keep going and going, then nobody respond. Then I'll just be talking and talking. Nobody can actually hear me. Okay, anyway, let's come back to our discussion. So we have established this continuity equation that we now apply to our second non-equilibrium condition, right? As we mentioned, the reason being that in the case of the second non-equilibrium condition, there is now a current component that's also flowing in the semiconductor, which we need to take into account as well, because if there's a non-uniform flow, right, that can actually change the rate of change of the carriers in the semiconductor as a function of time. Okay, so that's why we have to derive the effect of that, and we say that now to analyze the second non-equilibrium condition, we can now use this continuity equations, okay, that we have obtained. Okay, so this is the second non-equilibrium condition that we'll be studying. So as you mentioned, we have this piece of semiconductor where if we were to inject carriers at one end, so like, for example, like shining light just at the end, right, then you can create extra carriers at the edge, which then would start to diffuse and recombine as they get into the semiconductor. So the question we're asking is, what is this function for the excess carrier as a function of position in the semiconductor? Okay, so as this graph that's shown below, right, if you're to solve it under steady state condition, right, you'll find that the excess carrier, as it diffuse, they recombine, so the concentration actually would decrease, right? You expect it to decrease as it diffuse in the semiconductor, okay, because there's recombination involved. And later on, we'll see that from our analysis, this concentration will basically decrease, in fact, exponentially with position into the semiconductor until at a sufficiently large distance into the semiconductor, you drop back to the thermal equilibrium concentration. Okay, so in this analysis here, right, take note that we are basically assuming that the electric field is zero. That means there's no electric field throughout the semiconductor. It's just a purely diffusion process. And at the same time, we'll also be assuming that the two conditions that we used previously is also true here. That is, the majority carrier is much greater than a minority carrier, and that your excess carrier is much smaller than the majority carrier. That means a low injection condition. Okay, and in fact, our analysis will also be just focusing at the steady state condition. Okay, that means you inject carrier at the end and you give it enough time to stabilize, right, so that it doesn't change with time anymore. And we want to find out what is this delta P with X in the semiconductor. Okay, so there's a few sort of constraint that we're putting here. Okay, so starting with the continuity equation for holes. So obviously in this case we're looking at n-type semiconductor, and we inject extra holes at the end, right? If you use this whole continuity equation, which basically analyzes how the minority excess carrier change with time. Okay, so under this steady state condition, right? Steady state condition would mean that the this concentration of holes will not change with time. Okay, so steady state condition will mean that this term here actually goes to 0. Okay, then we need to put in the other terms, right, to try and analyze and see whether we can get an expression for delta P as a function of X. Okay, that's our objective. Okay, so using this continuity equation for holes, right, and obviously, there's no optical excitation. Yeah, so this GL is also equal to 0. So what we're left with on the right-hand side is 3 terms, GTH minus R, and we have this, component that's due to current flow in the semiconductor. So in the case of n-type semiconductor, the GTH minus R, just this term, right? We can actually, okay, because there's this two term there, we can actually simplify this to, if you expand it out and put in the expression for N and P, and you expand it out applying the two conditions, right? Where majority carrier is more than a minority and the excess carrier is less than the majority carrier, that means low injection condition. You can simplify this term to minus delta P over tau P naught, okay, which we have done previously, right? In the case of the optical illumination scenarios, okay, you can actually show that it's equal to minus delta P over tau P naught. So in other words, we can replace this two terms here, right, with delta P over tau P naught. And in terms of this current term, okay, because we said that there is no electric field, so you're not going to have drift current, okay, so this J of P of X, okay, J of P of X would just simply be due to diffusion. So we know diffusion current for the case of holes is this equation here, minus Q dP and the partial derivative of P with respect to X. Again, we put it as partial derivative because this P here, you know, strictly speaking, will be a function of time and position in the semiconductor. Okay, so when you write the derivative, you have to write it as partial derivative. Okay, so we can now put this into your remaining continuity equation, right? So if you do that, okay, if you do that, then you have you know, this range of terms here, which is equal to 0 on the left hand side. Okay, because we say this is steady state condition. So notice that the derivative terms, right? We put it into the derivative term. So you see here, we have the partial derivative of the current density with respect to position, and we say that the current is just the partial derivative of concentration. So if you put this in, you actually get a second order partial derivative of concentration. Okay, that's why we get this, you know, del square P over del X square. Okay, so it's a second order expression here, right? Second order differential equation here, which is this term here. Okay, so okay, similarly, this P here can be written as P naught plus delta P. And if you differentiate the delta P naught, okay, you would get 0. So if you do second derivative of P naught, you also get 0. So really, this term will disappear when you differentiate it. And this second derivative of P is essentially the same as the second derivative of delta P. Okay, now this gives us effectively second order partial differential equation, right? So it's not the standard differential equation that you're familiar with, because now our function is multivariable, it's x and t. Okay, that's why we have to write it as partial derivative. But anyway, this is kind of essentially a second order differential equation. All right, and in fact, if you treat it as a steady state condition, okay, with steady state condition, then the time factor is gone, right? So this delta P is just a function of x. Okay, and we can sort of change this to just a standard second order differential equation. So it's just d squared delta P over dx squared minus delta P over dP and tau P naught equal to 0. Okay, so there's a second order derivative. Okay, that makes this equation a second order differential equation. Okay, I think has everybody learned this already in your H2 math, the second order differential equation? Anyone has learned this already in H2 math? Or it's not in syllabus anymore? Anyone?
It's no longer in the syllabus, but
Okay.
some of us have learned it.
So you learned it. Okay, that's fine. Okay, so anyway, So that's essentially why I have this other slide here, right, to explain to you how to solve a second order differential equation. So because this is not covered in your H2 math anymore, okay, for the past few years, we will not test you on derivation of the solution for this second non-equilibrium condition, okay, because you never learned this, so we're going to test you. But anyway, we're going to give you the approach to solve this, right, so that you have some idea in terms of how the solution come about. Okay, just try and appreciate. So you talk about a second order differential equation, right? It will take this form that you see here, right? You have essentially the second derivative term, right? So here we have written it as y and x. Okay, so you have some term that is a second derivative of y with respect to x squared, right? And this a, b, and c are essentially constant values, okay? So this will comprise of the second derivative of y, and then the derivative of y and the y function itself. Okay, so if your second order differential equation can be written in this form where it's equal to 0, then we call this a homogeneous second order differential equation. Okay, so how do we solve for this equation? So the objective here is to try to find out what is y as a function of x. Okay, in other words, solve for y, right? Okay, because now you have a derivative terms, how do you solve for y? So for this type of homogeneous second order differential equation, okay, there's an approach that you can do this. So first we write this second order differential equation as an auxiliary equation, okay, replacing the derivative by a quantity or a variable here called m. Okay, so if you see two derivative, then it corresponds to 2m, okay, and that gives you m squared. If it's just one derivative, then we just have just one m. If there's no derivative, then we just put it as 1. Okay, so in the case of function y, we just put it as a value of 1. So we have am squared plus bm plus c equal to 0. This is called the auxiliary equation of your second order differential equation. Okay, so for this auxiliary equation, okay, what we need to do here is to try and find out what's the value of m. And this shouldn't be too difficult for you because this is just a quadratic equation, right? So there's actually a formula that you can use. And there are various possibilities for this m value. Okay, so in the case where the m value, right, or the roots are real values, but they are different in values. Because so in general, if you apply the equation, you can have two solutions, right? Okay, two values, let's say m1 and m2. If this m1 and m2 are actually real values, okay, and they are not of the same value, then the general solution for this second order differential equation will be given by this expression here. Okay, so the solution for y will be some constant c1 multiplied by exponential m1 of x plus c2 multiplied by exponential m2 of x. So that's the general solution of the differential equation. Okay, so in fact, if you differentiate this, right, you differentiate this twice, and then you put in the various derivative into your differential equation, you find that the sum of it will equate to 0, right? That means it satisfies this differential equation here. So in the case where the roots are real and unequal, then you get this general solution. Now in the case where the roots are real, but they are actually equal in value, which is possible, right? Because remember the solution for this, if you apply the formula, so your m will be minus b plus minus square root b squared minus 4ac, right, over 2a. Okay, so if your values in this square root term is positive, okay, then you will have real and unequal roots. In a case where this value in the square root term is actually equal to 0, then you find that your root is just the same value, right? It's minus b over 2a. So it's a repeated root, okay? So in this case, then the solution, general solution for your differential equation will be e to the power mx right, which is the common root, and then we need to add in this polynomial here, c1x plus c2, okay, where c1, c2 are some constant. Okay, so that's for the other scenario where the roots are real and equal. Now, there's also another scenario where this value in the square root term, right, what happens if it's negative? If it's negative, we take the square root of negative, we get imaginary numbers, right? So in this case, the roots are no longer real. Okay, they are actually imaginary roots. Okay, so the roots can be generalized as p plus minus square root I, where I is your square root of minus 1, right? The complex number. Okay, so if it is of this form, okay, if it's imaginary and it's of this form, then the general solution will be this, right? It will be e to the power of px, right? The real part of the root, and the imaginary part, the q, goes into this trigo function, right? You have c1 cos qx plus c2 sin qx. Okay, so these are the three possible solutions that you will get. Okay, if you solve this second order differential equation. Okay, so these are the approach, okay, to solve the second order differential equation. So if you refer back to what we have, right, which is this, right, this equation here. Okay. Okay, so we look at the actual equation that we have. Okay, let's clear this. So the actual equation that we have is d square delta p over d x square, and then there's a minus delta p over tau p naught, right? Okay, so this is equal to 0, correct? Okay, so it's this, sorry, d tau p. So there's a d there, missing d. Okay, dp tau t. Okay, so with this expression here, if you follow this rule, okay, then you can see that your a is equals to 1, right? Your b, there's no derivative of delta p, so b is equal to 0. And your c is minus 1 over dp tau p naught. Okay, so here you treat the delta p like y, right? Okay, so with these three values, and if you apply the formula to solve the auxiliary equation here, right? Your auxiliary equation will be m squared. B is 0, right? Then you have a c minus 1 over dp tau p naught. That means your m, okay, your m, in this case you don't have to use the formula because it's straightforward, right? You bring the value over, then you do a square root of this, then you have m as so there should be a plus minus because it's a square term, right, on the left hand side. So it's plus minus square root 1 over dp tau p naught. So this falls under the first scenario, right, where the roots are real. Okay, there's no square root of minus 1. It's real, and the two roots is plus and minus, so they are actually two different values. So the general solution, okay, for our analysis here will be of this form. Okay, so, and that's why over here we have delta px as a of exponential x over square root dp tau p plus b exponential minus x over square root dp tau p. Okay, so it's a real and unequal roots. Okay, then of course the other thing that we need to do here is to find out what is the unknown values of a and b, right? So you have actually boundary conditions that you can apply. Okay, where at x equals 0, okay, the excess carrier we can denote as delta p of 0. So this is value that sometimes we know, right? So we just say that it's some delta p of 0, which is a constant value. And the other boundary condition that we know, of course, is that when you go deep enough into the semiconductor, okay, x equals infinity, far away, then all the excess carrier will have recombined, then you will expect the delta P to be equal to 0. Okay, because it goes back to the thermal equilibrium concentration. Now, so you apply this, right? Apply this, you can find out what's the A and B. Okay, specifically, if you first apply the second boundary condition, right? When x goes to infinity, when x goes to infinity, this term here will be minus infinity. Exponential of minus infinity actually gives you 0, so this actually goes to 0. Okay, and what you have left here is this, where it's actually equals to 0 when x goes to infinity. So, you know, for this right hand side to go to 0, because this x here is infinity, right? Exponential of infinity actually gives you a large number. You know, for this, the remaining first term here to go to 0, your A obviously must be equal to 0. Okay, so applying the second boundary condition, we establish that A is actually equal to 0, right? So that is, that will basically say that, you know, the first term actually is gone, right? And what you have left, what you have left is the second term. If you apply now the first boundary condition, when x equals 0, okay, the left-hand side here is delta P of 0, right? Some known quantity. And if x equals 0, you take exponential of 0, this goes to 1, right? Which means that the B must be equal to delta P of 0, okay, some known value. Okay, so if you apply this to boundary condition, then we can conclude the solution now, the delta P of x, right, is just delta P, x equals 0, and you have this exponential x over square root d tau. Okay, and this square root d tau is basically a length quantity. We denote this as LP. Okay, this LP is called the minority carrier diffusion length. Okay, square root d tau is known as the minority carrier diffusion length. So it's a quantity that describes on average, you know, how far the minority carrier will diffuse before it recombines. Okay, kind of similar definition to the minority carrier lifetime, you know, how long it takes for the carrier to recombine, right, for it to exist before it recombines. Okay, so the solution of this is an exponential function, right? So you expect the excess carrier, okay, you expect the excess carrier to decrease exponentially with distance into the semiconductor, right? It's a negative exponential negative x, so it's an exponentially decreasing function into the semiconductor. And take note that this is for steady state condition. Okay, steady state condition. We will not be analyzing all the other different types of condition because you know, those will be a little bit more complex. So it's you know, not quite suited for this sort of introductory course to semiconductor. Okay, so we're not covering that. But with this, it's actually sufficient to go on and analyze, say, PN junction, and from there deriving the current that's flowing in the PN junction, right? You can derive the diode equation from there. Okay, that's more than enough already. All right. So similarly, if you consider the other carrier type, right, the P type, and you look at the minority electron, and you apply the continuity equation for electrons, okay, and you run through the analysis, you would similarly derive excess minority electron concentration as a function of distance into a semiconductor for steady state case. Okay, you find that the form it's you know, similar to that of the whole one. Okay, of course in this case because you're looking at electrons, so this characteristic length at the denominator must be related to that of electrons. Okay, minority electron diffusion length in the semiconductor. All right. So, okay, that kind of more or less conclude the second non-equilibrium condition, which involve injecting carrier at one end of a semiconductor and deriving the excess carrier concentration as a function of distance into the semiconductor for steady state case. Okay. Of course, in our discussion there, we, you know, have actually been talking about excess carrier under direct band-to-band transition. Okay, that means electron basically go from conduction, or rather from valence to conduction band, and then when they recombine, right, they go back down to the valence band. So it's a direct band-to-band transitions. Okay, so there's no defects that is considered in those cases, right? We are basically assuming an ideal semiconductor. But of course, in a practical case, you do get some defects in the semiconductor, and in some instances, you might find that the defect states are a lot. Okay, and in fact, it could dominate this transition process. Okay, so the transition may, if let's say the defect is a lot, the transition may actually go through the defect states. Okay, then you get this indirect recombination as well, right? Instead of direct recombination, you get indirect recombination. And in such cases, the question you may ask is, then how would the analysis of the excess carrier change, right, in the two non-equilibrium conditions that we talk about? Well, it turns out that in a case where you have indirect transitions, okay, it turns out that all we need to do is to just modify the minority carrier lifetime. Okay, we see that in the case of direct band-to-band transition, the minority carrier lifetime is 1 over alpha r p naught relating to the majority concentration, right? In the case of holes, it's 1 over alpha r n naught. In the case where you have indirect transitions, right, that's sort of an important factor there, then you cannot use the direct band-to-band transition lifetime anymore. Okay, you need to use this two expression here, right, relating to the trap concentration. Okay, because the trap concentration, if it's a lot, then it would dominate this the transition, right? So in cases like that, you have to take into account the trap concentration, and there's actually this constant term here, right, which are called, in the case of electron, the electron capture cross-section. The whole one is called the whole capture cross-section. Okay, this cross-section, it's basically referring to like the probability, okay? So it's used to quantify what's the probability that the transition will go through the traps. Okay, so you can think of this as like probability terms, okay? So in fact, that's all you need to change, okay? And the analysis or the final expression is essentially still the same. Okay, all you need to do is to change the carrier lifetime terms, right, to the appropriate representation. Okay, everything else remains the same, as you can see in the subsequent tables. Right, so this table basically lists down the solutions for the different scenario that we talk about, right? So you see that for direct band-to-band transition, in the case of p-type semiconductor, right, you have the respective solution there. For steady state, for light switch off, right? If you're in direct transition, that's the important factor. Then you basically need to modify the minority carrier lifetime, and everything else, you see the forms of the solutions are all the same. Okay, the only difference is the value of the minority carrier lifetime. Okay, has to be modified to sort of in terms of the trap properties. Okay, but in terms of the solution, they are all the same. Okay, so the subsequent slides all kind of illustrates to you the difference, right? In terms of expressions and analysis, it's all the same, right? Only difference is that the tau value is different. Okay, you need to use the appropriate representation. Okay, so this is just to give you an overview, in terms of what happened if what happened if indirect transition is a dominant factor. Right, then you have to modify the minority carrier lifetime. Okay, the rest of the analysis is all the same. Okay, so there's one other thing that I would also like to just quickly discuss, which is what we call the quasi-Fermi level. Okay, so we discussed previously that in the case of semiconductor in thermal equilibrium, you have the Fermi level, right? That's determined from the equations, okay, the Fermi level equations. And in the case of thermal equilibrium condition, whether you use the electron or hole concentration, your Fermi level that you determine is essentially the same quantity. Okay. Now then the question is, what happens when you have a non-equilibrium condition? Okay, if you're non-equilibrium condition, obviously the electron and hole concentration now would change, right? They are no longer N naught, P naught. That means they are no longer thermal equilibrium values. Then, you know, if you were to apply these two equations, right, to find the respective Fermi levels, okay, you will not be expecting the Fermi levels that you determine in non-equilibrium cases to be equal now, okay, because they are no longer the same. So this Fermi level that you determine, right, using the non-equilibrium concentrations of the carriers in the semiconductor, they are no longer sort of thermal equilibrium Fermi level, right? So to distinguish it from the thermal equilibrium case, we call this the quasi-Fermi level. Okay, so this quasi-Fermi level is not the kind of like the true thermal equilibrium Fermi level, okay, but they are just Fermi level that is calculated to sort of relate to the non-equilibrium concentration. Okay, so yeah, so the bottom line here is that, you know, if you were to apply those equations, right, to non-equilibrium case, of course, strictly speaking, you shouldn't, you know, because it's not equilibrium condition anymore. But if you do apply, right, then the resulting Fermi level that you get is what we call the quasi-Fermi level, right, which is used to represent the concentration, non-equilibrium concentration that you now have in the semiconductor. And this Fermi level that you determine will not be the same, right, between the values that you determine from electrons and from holes. Okay. So to sort of appreciate, you know, what's the use of this, right? I think it's useful to just go through an example, okay, to see how it's being applied and what is the implication, right? So suppose in this case we have N-type semiconductor, which has majority carrier concentration of 10 power 15. Okay. And the non-equilibrium case, you have excess carrier concentration of 10 to the power 13. Okay, what is the initial Fermi level under thermal equilibrium and the quasi-Fermi level in non-equilibrium case, and indicate this level in a Venn diagram. Okay, so in other words, draw the Venn diagram. So for thermal equilibrium case, it's quite straightforward. We can find the minority carrier concentration using mass action law, Ni square over N naught. Okay, so the N naught is given here, 10 to the power 15, and the Ni is 10 to the power 10. So if you calculate that, you get 10 to the power 5 per cubic centimeter. Okay, so that's the standard calculation that we have been doing. So this shouldn't be a problem to all of you, right? So if you apply the Fermi level equations, okay, using the electrons and the hole concentration, the equilibrium one, then if you work through it correctly, okay, you find that the Fermi levels that you determine here, it's the same. Okay, both would give you the same position for the Fermi level. Now, in the case of the non-equilibrium case, okay, if you apply your Fermi level equation, okay, for the case of electrons, take note that now it's non-equilibrium, so we write it as EF NQ. Okay, the concentration becomes N naught plus delta N, and if you put the values in and work through, in the case of electrons, you get 0.2984 eV. So compared to the original from the electron, right, you notice that it is increased by a little bit, right, increased by 0.0002 eV. Okay, so this quasi-Fermi level for electrons, it goes up, which is not surprising because you have extra carriers for electrons. If electron concentration increase because of the excess carrier, you would expect the Fermi level to move up closer to the conduction band edge, right? Okay, so this is expected. Now, what about the case where you apply it to the non-equilibrium hole concentration? So if you apply this to the non-equilibrium hole concentration, then you find that the Fermi level now, right, it's actually quite different from the value that you determine under thermal equilibrium condition. So you see here that EI minus EF PQ, okay, is now positive, and it has a value of 0.179. which implies that the EFPQ is actually below EI. Okay, so we have to draw the Venn diagram now and put in the quasi-Fermi levels. For the case of electrons, okay, you see that it's slightly above the thermal equilibrium Fermi level. Okay, and like I say, this is expected because your electron concentration increased. On the other hand, in the case of the quasi-Fermi level for holes, right, you see that it actually drops substantially away from EF. Okay, it goes all the way down to EI, right, over here. And, this kind of reflect the increased hole concentration that you get because of the excess carriers. Okay, and this change is significant because if you think about it, right, the excess carrier that is introduced for minority carriers, although it is insignificant for the majority carrier, but to the minority carrier, the addition is very, very significant, right? And so much so that the concentration that's added, it makes it looks like a P-type concentration. Okay, that's why your Fermi level for the excess carrier now goes below EI. Okay, because with that kind of concentration, right, it's like a sort of P-type dope semiconductor. The whole concentration in a P-type dose semiconductor. So you expect this to go down a lot more because the excess carrier changes it significantly. All right. Of course, if you take out the excess carrier, right, if you remove the excess carrier concentration, then you expect these quasi-Fermi levels to collapse back to the thermal equilibrium one. Okay, so this quasi-Fermi level kind of indicate to you, the magnitude of the excess carrier that is contributed, right? Whether it's very significant in the case of minority carrier, in which case you get a big shift in a quasi-Fermi level from the thermal equilibrium Fermi level. If it doesn't create a lot of change, right, to the concentration like the majority carrier, then you see that the quasi-Fermi level just changes by a little bit. Okay. So so the consideration of this is useful because in fact this quasi-Fermi levels, right, if you look at the gradient of it, it is actually related to the drift diffusion currents in the semiconductor. Okay, so if there's a current that's flowing in a semiconductor, then you find that the quasi-Fermi levels will take on some gradient. And of course, if there's no current flowing, then the Fermi level will stay a constant in the semiconductor. Okay, so this is kind of useful, when you draw the Venn diagram to kind of indicate this effect, with respect to current. Okay, so the quasi-Fermi level is kind of to represent that. Okay, so in fact, in the tutorials related to this particular topic, I think there'll be a question that requires you to do some calculation on the quasi-Fermi levels. All right. Okay, so I think that's essentially all the topics that I am covering for the first half of the course. So from the next lecture onwards, Prof. Ang would take over. Okay, and he will similarly create this lecture calendar item, right, which you can then log in to do the lectures. Okay, so from next week onwards, you'll be learning about PN junctions and some of the other related devices, okay, and how they work, and also some calculations, to determine the current that's flowing in these devices, right, and the various electrical properties of the devices. All right, anyone has questions?
Hello, Professor.
Yep.
I have a question.
Mm-hmm.
That is regarding to the first part of the lecture. Sorry.
Yep.
For the decay of the initial excess concentration, there's an equation, right?
Decay of the first non-equilibrium condition, you mean?
Yeah. The equation suggests, because it's an exponential equation, it's suggesting that the concentration will only approach 0 but will never reach 0. Is it true?
It will reach 0. It will reach 0. It depends, of course, it depends on the magnitude of this minority carrier lifetime, right? And typically these values, right, will be in the range of micro to nanosecond. So obviously when we draw this, when we draw it like this, you must be aware of what is the sort of scale we are looking at here. If you draw it like this, then this scale that we're looking at, it's in the range of micro to nanosecond. So if we wait 1 second, then it's very, very long, and your excess carrier effectively is 0 already.
Then how do you determine what is the time that you will reach 0?
Well, I mean, in general, we say that it tends to infinity, then the question is, how much is enough, right? Then, you can basically look at this, right? So, whatever time you have, okay, and the probability where it goes to 0. So in this case, we would use the exponential equation that we have, which is here, right? Okay, so if you have this exponential equation, then it depends also on the magnitude of this, the delta n. Okay, so if delta n is, for example, 10 to the power of 12, let's say, okay. So if this exponential term goes to a value that is less than 10 to the power of 12, then the product of it will become a fraction, which means that, effectively you can treat it as 0 already, because number of excess carrier cannot be fraction, right?
Yeah.
You know what I mean? Yeah. So so up to a certain range, effectively you can treat it as 0 already. So in fact, if you take some arbitrary value like 10 times, or even 100 times, effectively you probably can treat it as 0 already, from the minority carrier lifetime.
Okay.
Yeah.
Okay, thank you.
All right. Any other questions?
Prof, hello.
Yeah.
Can you elaborate on steady state conditions and why the carrier concentration is constant with time? I don't really get it because there is low injection at the same time, which indicates that carrier concentration is increasing.
Hi, Prof. You're muted.
Okay. Right. Okay. Sorry. So right. Okay. So if you think of the thermal equilibrium case, we have a generation process, right? Thermal generation that adds carrier to the semiconductor. We have the recombination, which removes carrier from the semiconductor. So under thermal equilibrium condition, the thermal generation rate will be matched by the recombination rate, which then gives you a 0 net increase in the carriers in the semiconductor. So the N0, P0 become a constant value, right? There's a balance between the thermal generation and recombination. Now in the case of with optical illumination, right, the instant when you add the optical illumination, you have the generation rate larger than the recombination, right, at the instant when you have optical illumination, and you have a net increase in the carriers. Okay, that's why this concentration here increase. But bear in mind that if you have a net increase in the carriers, right, the R will not stay the same, because remember R depends on N and P. So if one of the concentration increase or both increase, then the R actually will also increase, right? and you actually sort of try to cancel out this increase in the combined generation rate. So after a sufficiently long time, right, this increase will give you an R that will match the recombination until they will stabilize. Okay, and at this stage, whatever that's added, right, by the thermal generation and the optical is balanced by the recombination, and then this will become a constant. So the reason why it doesn't keep increasing is because the recombination would in turn increase as well to balance it.
Okay. Thank you.
Yeah. Okay. Any other questions?
Hi, Prof. I have a question.
Yeah, sure.
So regarding the general equation for minority carrier in the earlier slide for indirect transitions, why is the thermal generation rate of the carrier not considered in the equation?
Sorry, for which one? Which one?
The general equation for minority carrier, like the slide is a table showing equations for direct band-to-band transitions and indirect transitions.
Direct band here?
Yeah, this one.
Okay. Which one is not considered?
So on the top right, it's just GL minus recombination rate. But what about the thermal generation rate?
Oh, okay. So this is okay. This is actually written where this R prime, right, is the GTH minus R.
Oh, okay.
Yeah. So the GTH is embedded into the R prime already.
I see.
Yeah. That's kind of another way of writing it. It's the net recombination. But actually the GTH is there. It's in the R prime. So the expression is actually the same. Okay. Any other questions?
Hi, Prof.
Yep.
I have a question regarding the quasi-Fermi level.
Yeah.
Can you go to the second last slide?
Okay.
Okay, so just now you mentioned that the quasi-Fermi level for the holes, right, falls below the E intrinsic, so the semiconductor behaves as a p-type semiconductor, right?
Well, no, it doesn't behave as a p-type semiconductor. I'm saying that the concentration of the minority carrier now is like that of a p-type semiconductor with a Fermi level position at that of the quasi-Fermi level for holes. Just the concentration is like a p-type semiconductor with that Fermi level.
All right.
Yeah. So in other words, the quasi-Fermi levels are basically to just used to quantify the corresponding non-equilibrium concentration. So it doesn't indicate the thermal equilibrium concentration. So it's only applicable to concentration of that particular carrier type that is representing.
Okay.
Yeah.
Thank you.
Okay, so if there's no more questions, yeah, that's it for today. So take note that the list of formulas and table of physical constant has been uploaded into the course site, so you can have a look at that to have a feel of what are the equations that are actually provided in the formula list. The physical constants are all given there, so you don't really have to memorize the table of physical constants. Okay. For those who are attending labs, right, in the subsequent, in fact, tomorrow and the subsequent weeks, the lab manual has also been uploaded. So please download a copy, print it, and bring along for your lab class. And bear in mind that this lab 2 and lab 3 are graded. Okay, so you first of all, have to come for it. Of course, if you have valid reasons, like if you are sick and you have MC, right? Then later on, we'll see how many there are that didn't come for the lab class. We would basically arrange for makeups. Okay, so that one we will let you know a little bit later. Okay, but when you come for class, do try to be prepared. Okay, because this is graded, and there is also a formal report that you need to do. Okay, so who is supposed to do a formal report? When you come, we'll tell you. Okay. Ken, okay, there's no more question, then I guess we'll end here for today. Anyway, along the way, if you have some queries, right, during tutorial class, you can also raise it to us, and we can try and answer some of the questions you have. Okay, so if not, then yeah. Sorry?
Professor, can I ask if we can view the sample lab reports during tutorial?
During tutorial?
Yeah, view the sample lab reports.
Okay, you are from which class?
The lab one.
Okay.
L1, good one.
Oh, so you came for the first class, is it?
Yeah.
Okay, but you didn't get to see the report, huh?
Yeah, didn't really have the time.
I see. Okay. Yeah, we can try and bring that. Okay, I'll try and bring that.
Thank you.
Okay. Okay, so if there's no more question, then I think we can end here. All right. Thanks, guys.
Thank you.
Okay.
Thank you.
Thank you.
Okay. See you guys.
Thank you, bro.
Thank you.
Thank you.
Thank you, bro.
Thank you,
Okay.
Prof.
Bye, guys.
Thank you, bro.
Okay.